Alright guys, welcome back. This is part 3, the final part of our second example for the three-moment equation. Picking up exactly where we left off, just a quick recap. We just found all of the internal shears and moments basically on each end of the spans. And just to remind you guys that this is for this problem up here. It's a 3-span beam. It's 2 degrees technically indeterminate. And yeah, we're ready to draw the shear force diagram and bending moment diagram for it now. So if we just set up the shear force diagram first, then we can go ahead and plot on all of the shears at each end of the spans that we know. So on the very left-hand side of span AB, we found that the shear VA is positive 17.817 kilonewtons. So let's throw that on. Let's say that this is going to be about 17. So this is 17.817. We don't need to write kilonewtons because we got it right here. Okay, so when we move over to the other side, we found that the shear just on the other end was negative 32.183 kilonewtons. So we can drop it like that, and then we know when we're drawing shear force diagrams that as long as there's no distributed load or point load, then the shear is going to be constant in that region. So basically, from this point until we go out and hit that point load that was 5 meters across the span, we're maintaining this constant shear. And same on this side. The shear is not going to change until we experience a change in force as we go along, and that's going to be at that point load, so we can connect them like this. And the cool thing is, let's try and draw that a little bit cleaner. The cool thing is if you add up the total change in shear, so 17.817 plus 32.183, it actually is equal to a change in magnitude of 50 kilonewtons, and that is exactly what's happening because we're jumping by 50 kilonewtons where we have this applied load. Alright, so when we look at the next span BC, we found that the shear basically on the left-hand side was VB2, or just to the right of the support. We found that to be 34.317 kilonewtons, and that was positive. And then on the right-hand side of VC1, we found that to be negative 15.683. All right, now the same thing applies here. So our shear is going to be constant until we hit that point load that's 3 meters out along the span. And then same thing here, this shear is going to be constant until we hit that point load. So that's going to drop us down like that. And then we can go and connect all these dots as well. And again, if you look at this, 34.317 plus 15.683, that jump that we're getting that's pushing our shear force diagram down is going to be equal to 50 kilonewtons, which means then that the jump up here is going to be equal to our reaction force at B, basically. But we'll get to that in a second. Let's finish drawing the shear force diagram first. So in section CD, we found that VC2 is positive 57.867. And then the shear at D was VD, that's negative 42.133. So we can go ahead and connect these 2 points first because we know there's going to be a big jump up there for the reaction at C. And then we know that this in this region, the shear falls linearly by 10 kilonewtons per meter as we go along. Or what we can do is just acknowledging that it's a constant distributed load, that we just connect these dots basically. The other thing that you could check if you're curious is the total change in magnitude of the shear as we go through this distributed load. The total force caused by the distributed load is 100 kilonewtons because it's 10 kilonewtons per meter times 10 meters. And then sure enough, if you take this total change in magnitude, you have 57.867 plus 42.133. That is 100 kilonewtons. So just nice checks to do all around. All right, so let's just close this off, and that's going to bring us to the end of the beam. And then let's label on these distances as well, just so we don't get confused here. So this was 5 meters, this was 5 meters, this was 3 meters, this was 7. Now we don't actually know this distance, but we can easily find it by similar triangles. So we got 5.7867 and 4.2133 for this section. All right, so the next thing that we're going to want to do is we're going to want to figure out what all of these areas are on the shear force diagram. So we're going to take these areas as the change in magnitude basically on the bending moment diagram as we move from left to right to each of these points, where positive areas will be positive changes in magnitude, negative areas will be negative changes in magnitude. Constant sections are basically like horizontal lines on the shear force diagram are going to give us linear changes on the bending moment diagram, and then areas where we have linear changes in the shear force diagram, we're going to have parabolic changes in the bending moment diagram. Alright, so we know that we're going to start at 0 because it was the end of a span, and in this region we have linear change bending moment diagram, and it's going up by the magnitude there of the area, which is 89.085. Now as we go from this point to this point, with change in magnitude on the bending moment diagram is equal to this area. So what we do is we take 89.085 minus 160.915, and that brings us down to negative 71.83. Alright, so now we take the next area, it's a positive area, so our change in magnitude is going to be positive. The change in magnitude is 102.951, so we add that to negative 71.83, and we get 31.121. And then for the next section, we have 31.121 minus 109.781, and that's going to bring us down to negative 78.66. And then for this next region, we have a positive change in magnitude, but we need to have a parabolic shape. And basically the parabola is going to peak out right here at this intercept, because once we cross that, the area becomes negative, and then we start getting negative change in magnitude. So negative 78.66 plus the area 167.429 brings us up to a new value of 88.769 at the peak of that parabola. And then when we go and take our last section here, negative area, and subtract it, 88.769 minus 88.759, we're off by 0.01. Basically, that's just a rounding error, and this comes right back down to 0. So that's close enough. All right, so what we can do, if you're curious, we did find out earlier on in the problem, we calculated the internal moment at B, and we also calculated the internal moment at C, but then we found them graphically here. So let's just go up and see what we got for those. The internal moment, here it was. So we had MA was 0, MB was negative 71.833, negative 78.667, and 0. And if we just go and compare that to what we have on our actual bending moment diagram, yeah, we had 0, negative 71.83, some rounding there, and negative 78.66. So that's cool. That looks like we've done that right. The only other part that the only other thing that this question was asking for was the reactions. It wanted AY, we wanted BY, CY, and DY. All right, so what we can do is we can look at the shear force diagram to get these. If we drew a virtual cut, basically starting at A and taking a virtual cut just to the right of it, we know that we have the reaction here, AY, going up, and we know that we have a positive shear, so it's oriented like this on the right-hand side of that virtual cut of 17.817. And so for the force balance to work, this means that AY has to be equal and opposite to that, so it's 17.817 kilonewtons oriented in the upward direction. Now when we look at point B, I think I mentioned this earlier where we had like the point load pressing down and we get the jump downwards in the shear force diagram. Well, when we have a jump upwards going left to right, that means that's due to a point load basically acting at that location, and that would be the point load caused by the reaction BY. So if we take this negative 32.183 plus 34.317, we're going to find that the sum of that is 66.5 kilonewtons, and that is also oriented upwards, right? Where we had the point loads pressing down, causing that downward jump. There was one there, and there was one there. Where we have the upward jumps, it's oriented upwards. So the same thing is happening at CY. We take the sum of these two values for the total jump. So 15.683 plus 57.867. And that gives us a reaction here at CY of 73.55 kilonewtons going up. And then lastly, when we're looking at the reaction at DY, again, if we do a little virtual cut in a free body diagram, let's draw on DY pressing up, and we're taking a cut just to the left of point D. So we have a negative shear at this point. So that negative shear on the left of a virtual cut would be pointing down. That's opposite of positive sign convention. And the magnitude of that is 42.133. So for the force balance at this point to make sense, if we're taking that cut infinitesimally close, that means that we have to have dy as 42.133 kilonewtons pressing up. And if you sum these up, you're going to find out that we're getting, the reactions are totaling 200 kilonewtons in the upwards direction. And if we compare that to the applied loads on this structure, which were way up at the beginning of the problem, we had 50 kilonewtons pressing down, 50 kilonewtons pressing down, and then 100 kilonewtons pressing down. So basically, if you look at the entire structure, you have 200 kilonewtons pressing down And we just found out that all of the reactions pushing up are like 200 kilonewtons pushing up. So that also kind of looks like we've done it right, because if we consider this whole thing to be in static equilibrium, then the sum of all of the vertical forces is giving us 0. So awesome, guys. If you watched all 3 videos, I really hope this helps. And thanks for watching, and I'll see you guys in the next video.